asking what was them that does believe essa question. My last participation in a scientific international will be also involved cosmology. Next year, I am visiting the Cosmos Institute after 54 years of working in the same laboratory. And later, I am moving to Israel to live with my daughter and grandchildren. And only 3 hours far from my son and principal. My position as head of the laboratory to Simone that I make sure that my work together with the Fernandes Masters with the I want to thank all the Berger that proposed my name and to the others that have been with me. It was a great honor and it's a great opportunity to say goodbye. I wish you all a good evening and a wonderful time in Rio.
Well, good evening, ladies and gentlemen. First of all, I'd like to state that I think nobody believes that we have been working for more than half a century in Rio and at the Global Cruise Institute. And I include myself anyway. As a general director of the Global Cruise Institute, and I think I can speak on behalf of the president of the Global Cruise Foundation. I'd like to welcome you all from different Brazilian laboratories and different laboratories from abroad for this meeting concerning monogeneia. For me, it's really a great honor to be in the opening ceremony, and because of this, it's really important for me to thank Walter and Anna for providing me this kind of surprising opportunity to be here. And of course, congratulate you all, the organizers and the participants, to be here for the next 5 days. I should confess that I'm strictly ignorant on the central theme of this meeting. Yet, I've just got the opportunity of reading something, and although I can be wrong, I think it's I realized the importance of this theme of the meeting. Not only if you think of economy as related to fish commerce, for example, but also, and I could see a little bit of the conferences and posters also concerning the biology of these words in terms of phylogeny and molecular biology itself and biodiversity. And I think that the insertion of these animals in biodiversity and in specific ecological niches is something that can be quite useful, not only in terms of the study itself of these animals, but also to provide ideas that can be applied for other experimental models or biological models. And it's so much important, it appeared to me so much important that not by chance the opening lecture will be devoted to discuss climate change and biodiversity. So for the next 5 days, I wish you all a very fruitful and scientific discussion. And I'm sure that this will be the case considering the numbers of posters and conferences that I could read in the abstract book, which, by the way, is spectacular. It's one of the most beautiful I have ever seen for the last 50 years, okay? So, but hopefully this can be associated with some leisure time. And I'm sure that you won't regret a barbecue here in Rio, as well as dancing in Lapa, which is very, very, very interesting. And don't miss it, because it's worthy. After, of course, scientific discussions, and perhaps between one or two dances discussing a little bit, which is also, and of course, discussing science together with 1, 2, if not 10 caipirinhas is quite useful. So I really wish you a very, very nice meeting. Thank you.
Several things to talk to you. First of all, is that, again, we're thrilled to have you here. This is the first ISM in the Americas, by the way. And we're happy to bring you to Brazil. And I hope it comes back. To me, that's a good idea for you guys in Argentina, perhaps one day. Bariloche is a very place too. We wanted to make this meeting in Rio because Rio has a special meaning for all Brazilians. This is a special place. No wonder it's called Cidade Maravilhosa, it's a wonderful city. We had a little bit of argument at the beginning, right? Because it's cheaper in Curitiba, but then Simorian said that everyone is going to be chill there. It's going to be very cold. So we have been blessed with this beautiful weather, and it's going to be a great weather throughout the Could you run those photographs? Michelle, you run mine? I need to control, right? So I just want to remind us of some of our history, ISM history. And there are some people in this room that have been in some of these ISM meetings before this one, including many people from the first one. That includes Donna, right? Elon, who was in the first one? Guru was in everyone. And Earl, go back. Go back. I just want to, no, not this one. Something wrong with it. Is it good? That's right. While you see back there, there's a camera that will be filming the entire meeting, and it's going to be streaming online. So if you want to call your friend, we're going to be streaming the entire presentation for people that couldn't come. And when I first saw our list of people, I said, well, too bad we don't have Jack Llewellyn anymore. We don't have Warren Malmberg anymore. Graham Kern is not here. Some of them are deceased. Torbaki is not here. Some couldn't come. Ian Whittington couldn't come. Bill Harris couldn't come. And I said, well, we're missing some of the big guys, right? Then I figured out that some of the big guys are right here. Times, well, there's a music in Brazil that says that times never stops. And what we have now is Jack Llewellyn in the training of some of you. We have Monsieur Z, Representative Z, in the training of many of you. And then they're still here. Some of them are still here. So we continue to change the composition of this group. And we are thrilled to have new people like Gustavo, like Tini, and so many others from places and first comers from ISM. So it's really nice to have you guys here, every one of you. And I hope we continue getting together every 4 years or so. It would be nice to do less than that. we have planned this entire week, not the entire week, but scientific program, but we have tried to organize the scientific program in such a way that we have different subjects being presented throughout the week, and not blocking. Let's talk about jaguars one day, except for one group of animals, which is the worm of the hour, right? Jaguars was the worm of the hour in others ISM, this time it's Typhlosion. And of course, Milan, there you are, is the one that's going to chair this section, and it's going to present some interesting work for us. You probably already saw the abstract. The abstracts are full of great work, so we're going to have a lot of fun. We have organized also 2 round tables, and one of the reasons we did that was to force or suggest collaboration. I think it's time for us to start collaborating a little more than we do already. I think Dan Brooks is right there. He's going to be giving us a seminar in a little bit, and he's going to talk about how complex the biological system is. And there's no other way of solving some of the problems of biological systems, dealing with biology, whatever, especially for us biologists, without collaboration. So we are indeed trying to suggest collaboration during this thing. And the round tables have this objective. And on Wednesday, get your shorts, get your bikini, in a hat, and let the sun tan on the beach. So on Wednesday, we're going to have we're going to leave at 10 o'clock from the hotel, right in front of the hotel, so we can drive somewhere else this coming year. We're going to leave and go by the ocean and to a very relatively secluded beach on Rio. Yes, we still have that in a nice little farm, and we're going to have a typical Brazilian barbecue with lots of caipirinha and try to behave yourself. But we're going to have a lifeguard. It's not a big problem. On Thursday, we're going to Lacla. And Lacla is where the samba is. If you've heard of samba, samba is one of the typical music in Brazil. And I'm certain many of you already be dancing like Louis Dupree is. Louis was in a samba school yesterday, and if you need any tips, how to dance. I would really like to thank all of you that was back on the ISM6 and voted for Brazil. I hope we can make you happy during this weekend, this week and the weekend, and the days after. And I think we're going to stop talking too much, and I'm going to allow Dr. Dan Brooks to give us the first trying to start a tradition here, and we call this the Alexander Gusev Memorial Lecture, which is a lecture that we are suggesting that it could be offered in the first day of the opening of ISM. And Dan Brooks is a personal friend of mine. He is a person that influenced my scientific life for many times. Every time I meet him, I said, oh yes, I should have thought of that. So he's my oh yes friend. Dan is now at the University of Nebraska. It's a very famous parasitologist. Most of you have read about him or read his work and his books. He has changed the ideas of parasitology in many areas. And he's going to be here with us talking about the parasites and climate change. I think his talk will cause some input for us, and we're going to be talking about this probably with the beginning and afterwards. Then, would you take over? So, thank you guys. Welcome to Rio, and let's have fun. As always, as we always did. And if you saw, I didn't say monogenia not once. That's the whole joke. some people that we have time. Fine.
The analog method. Yeah, I have the hard drive on my laptop died in April when I was visiting a colleague in Munich, and one of the graduate students there said, "Oh, this is a disaster. What are you going to do?" And I said, "Well, I have the old analog method." And he said, "Oh, I heard about that, but I heard that the resolution's not very good." So tonight, I'm also not going to mention Montesquieu in particular. That's because after almost 40 years of being a professional scientist, I've learned that one important lesson is that you never walk into a room of specialists and try to tell them anything about what they are specialists on. So I'm not going to give you any thoughts about your particular organisms, but I'm going to try to suggest some general themes that may be applicable. And one of the things that Eric Hoberg, the curator of the U.S. National Parasite Collection, and I have been publishing a lot about in the last nearly 10 years now. We've been both of us, Eric in the Arctic and me in the tropics, we've been working probably for 20 years now. We've been convinced that of two things. The first is that the issue of climate change and the biodiversity crisis and emerging parasitic disease is basically all one problem, and it's a really important problem. It's a critical issue to be addressed. And at the same time, we've also come to believe that parasitology really is in a position to make great fundamental leadership contributions in this area. And one of the things that we're lacking is a unified framework, and another thing that we're lacking, of course, is some kind of consistent approach towards collaboration and cooperation. As Walter said, we'll talk about that later in the week. So one of the things that we need to do if we're going to have a productive general framework that parasitology can present to the rest of the world and say, we have something important to say, we have important perspectives, and we have something to offer that is not trivial. In order to do that, in a sense, we have to have our own affairs in order. We have to have a very consistent perspective on what the results are really saying. I've said some of the students who are Chiba who are here have heard this before a year ago when I was teaching here, but one of the mistakes that biodiversity people have been making in the last 10 years, I believe, is that we have thought that we need to make the public and make politicians afraid, in a sense. We have to make them take this seriously. And we have believed that the lack of appreciation, the lack of action on the part of national governments in particular is due to the fact that people don't really understand how serious the crisis is. But in spending time speaking with people, now that I live in a part of Nebraska where many people, there are more people in Nebraska who believe in angels than believe in evolution, let's say. So this gives you a different perspective on the world. And I've actually had the opportunity to speak at length with people who are what we call climate change deniers. And what I've discovered is that one of the main reasons for denying the reality of climate change or denying the basis of climate change now is actually fear. And in fact, we've done too good a job. We've made people so afraid that they don't want to hear about it anymore. In other words, we've done such a good job of making people afraid that they're in denial. And so one of the themes that I developed last year when I was teaching in Curitiba and Maringá was this idea that we need to begin going to the public and instead of saying, be afraid, the crisis is coming, your children are not going to have the internet. I say this sometimes. I say that my grandchildren may ask my My great-grandchildren may ask my grandchildren what kind of fish you catch with an internet. I said, no, an internet was this magical thing that was in the air and you couldn't see it, and everybody could talk with everybody all around. Yeah, Grandpa, I know this. We know that's a fairy tale. But this is a very real thing. Well, what we now need to do is to say, it's serious, it's real, but don't be afraid, we have a plan. Now, in order to have a plan, we have to have a very good sense of what's really going on with the basic biology of our organisms. And one of the things that Eric and I have been trying to promote is the idea that climate change and the climate change crisis, the biodiversity crisis, the emerging disease crises are not crises of ecology and genomics and vaccines. In fact, this is an evolutionary phenomenon. And fundamentally, it's an evolutionary phenomenon which includes within it an ecological context, a pathology context, an adaptational context. So, we begin with this. I always like to, this is some of you who are as old as I am, will know that 30 or 40 years ago when phylogenetic analysis was a horrible thing that no reasonable human being would want to do, the people like me who were trying to promote phylogenetics and parasitology oftentimes were met with great aggression and responded with great aggression. Well, as you grow older, you begin to realize that what you want to do to have an effective conversation is to begin with something that we all agree on. So here's something that virtually every parasitology textbook will say, virtually every textbook that talks about parasites will say. Most parasitologists believe this in one sense or another. We're not. The framing is not so good. I mean, part of the problem is that the resolution on these Mac monitors is greater than the data projector. Anyway, I'll fill it. Okay. So most parasitologists, most of us agree that parasites are ecological specialists, whatever we mean by that. When ecologists talk about terms like generalists and specialists, it's the same thing as when systematists talk about species. Okay? Everybody has a really good idea about what they feel about that, but nobody really wants to talk about it very much. Because once you begin discussing it, you find out it's a very complicated thing. So when people say that parasites are ecological specialists, generally they speak in terms of microhabitat preferences and transmission dynamics, life cycle patterns. Okay. Now, oftentimes we've used, especially parasite ecologists, have used the number of different host species utilized by a given parasite as an indication of whether or not a parasite is a generalist or a specialist. And one of the things I'm going to suggest to you is that of all the criteria that we've used for thinking about parasites as specialists or generalists, this is the worst one we could ever have used. And the insect plant people also use this criterion a lot. And a group of friends of mine at Stockholm University are fighting that fight with the insect plant people, saying host range doesn't mean anything. And I'm going to show you why. It's because host range, when you view it from an ecological perspective, it looks like one thing. But when you view it from an evolutionary perspective, there are extra dimensions to it that we haven't fully integrated into our worldview. There are two sort of major conceptual platforms that are being used right now in talking about things like emerging diseases. One is the assumption that all of parasite evolution follows this thing called a coevolutionary arms race. Now, for those of you who are really young in the audience, this doesn't really mean too much to you, but the reality is that the coevolutionary arms race was an idea that was proposed by a couple of Americans in the 1960s in direct analogy with the struggle between the Soviet Union and the United States with respect to building weapons. And it made sense to people because of the political context. However, I'm going to suggest to you that this phenomenon exists, but it actually has a different context, a different significance than we thought. It's not nearly as important as we thought. But the coevolutionary arms race model basically says that progressive specialization reduces between host and parasite, reduces the host range, the number of hosts associated with a particular parasite. And it also reduces the ability of a particular parasite to exist in different hosts. And one of the things that means, of course, is that if this is really what explains the evolution of parasites and hosts, it means that the coevolutionary process itself should be the greatest protection against emerging diseases. The only time you should have an emerging disease is in an extraordinarily rare case of host switching, which can only happen when there is some sort of accidental novel genetic mutation for the ability to utilize a host that's never been utilized before, and the ability to get to that host and the ability to survive in it and that sort of thing. Now there's another more recent concept that we've been using called this is the concept of enemy-free zones. And this is something that it's one of these things that if you're not a parasitologist and you only think about it for about a microsecond, it sounds like a really cool idea. But if you think about it for more than a microsecond and you're a parasitologist, you realize that there's something not exactly right. The enemy-free zone concept says that parasites that migrate, that change their geographic range in response to climate change, hosts that change their geographic range in response to climate change, or hosts that are introduced to new areas outside of their native range, succeed in the new areas because they have gone away from the areas where they existed originally with a whole bunch of pathogens, and they've moved into a new area where there aren't any pathogens. And like I said, that sounds like an interesting idea, and there is some empirical evidence in short time scales that introduced species oftentimes do quite well. Okay. Now, one of the things the coevolutionary arms race and the enemy-free zone basically says that we should find very little evidence of host switching and geographic dispersal in phylogenetic studies of hosts and parasites. And we should also find very little evidence of it today. And if we do find evidence of host switching today, it's because something very unusual is happening right now. What we're seeing today is not the result of something that has happened before. Now, the paradox, what Sal Augusta and I call the parasite paradox, is that parasites are ecological specialists with all those things that are supposed to go along with being a specialist. And yet, every phylogenetic study that's ever been published shows substantial amounts of host switching. Even the studies that have been published that purport to show massive amounts of co-speciation and not very much host switching. Now, I'm going to show you an example of that later on. But every published study, unless you use a method of analysis that eliminates the possibility of host switching, so things like tree map or DIVA, if you don't use a method of analysis that eliminates the possibility of finding host switching, there's massive amounts of host switching. And the pattern for our organisms, parasites and vertebrates, turns out to be virtually identical to the pattern that the insect plant people find. So there is this parasite paradox, and in conjunction with this group of researchers at Stockholm University, which is basically 3 generations of researchers now, there is a unified kind of perspective. There's an alternative to the coevolutionary arms race. It doesn't have a name, which is really nice. Nobody started to fight over who gets credit for it. It's just a good idea right now. And this over here is supposed to say resolving the paradox. The first is how to explain differences in host range. Okay, if we're not going to say a parasite that's only found in one host today is a specialist, a parasite that's found in 20 different species of host today is a generalist, and yet we find a range of variation in the known host range, how do we explain that? Well, it turns out that if you do a large-scale phylogenetic analysis, the group in Stockholm did an analysis of host range over the phylogeny of Lepidopterans. So this is a large scale. And what they found was this wonderful pattern that they call the oscillation hypothesis. What you find through phylogenetic time is that host range increases and then decreases and increases and decreases. So just from that standpoint, you have this perspective that host lineages, parasite lineages go through periods where they become more generalized, more specialized, more generalized, more specialized. So that means that generalists become specialists, specialists become generalists, back and forth and back. So it's not a one-way street. So that's the first thing that we see, is that going from being a specialist to a generalist or being a generalist to a specialist seems to be something that happens all the time in evolutionary history. In addition to that, when we take into account phylogenetic conservatism in the ability to infect hosts and restricted geographic ranges for the origin of parasites, we begin to realize that this planet is full of parasitic species that have originated in one particular place at one particular time in association with one or a small group of particular hosts in one ecosystem. And yet, the hosts that they are inhabiting have very close relatives living in other places. And those other close relatives, because they are so phylogenetically similar to the hosts of these parasites here, those close relatives, even though they are not currently exposed to these parasites, nonetheless are already susceptible to them. And if the parasite is ever introduced into the area where those other hosts are, those relatives are, or if those relatives are introduced into the area where the parasites are, the parasites will not actually see them as a new kind of host. Only the biologists will say, oh, there's a new host species. But as far as the parasites are concerned, the new host species is just more of the same real estate. If you have 5 different species of fish living in one clade for many, many parasites, the gills of all 5 of those species of fish are probably more or less the same kind of habitat. And the only reason you don't find all the species of parasites living on all those species of hosts is because the species of hosts tend to be allopatric. Most closely related species don't live together. And so we think that there's very little potential for host switching, when in fact there's massive amounts of potential for host switching, because phylogenetic inheritance is very conservative, and closely related species share a lot of things in common. Dan Jansen called this phenomenon ecological fitting. Ecological fitting is this notion that you can go into one place and find one particular species. Jansen was working with insects feeding on plants, but the same thing's true for parasites and vertebrates, or any kind of close association like that. You go into one place, one ecosystem, one set of trophic structures, and you find one parasite species living there in association with just one host, or one set of hosts in a complex life cycle. But you go 500 kilometers away and you find the same species of parasite with also a one-to-one relationship in this other ecosystem with a different host. Now, if you're only studying here, you go, this is an extreme ecological specialist. It's only found on one host. This must be tight coevolutionary arms race stuff. You spend 5 years measuring the interaction between those two host species. You publish a PhD on the evolutionary arms race. And then 5 years later, another graduate student goes into this other ecosystem and publishes an equivalent PhD dissertation on exactly the same thing with the same species of parasite and a completely different set of hosts, draws the same conclusions over there, and together the two papers create a problem. Because each one of the papers taken separately makes it look like you've got these extreme specialists, but you throw them together, you go, oh, well, then they must be generalists. Well, no, they can't be generalists because, and the reason for this is because of ecological fitting. There is a massive amount of potential because there's all this evolutionary conservatism out there. So there are massive numbers of susceptible hosts on this planet that are simply not exposed to all the different species that they could, in fact, support at any one time. So now we come back to the coevolutionary arms race. It turns out that the coevolutionary arms race explains how host-parasite dynamics are maintained. So the arms race explains over in this valley how this species of host and this species of parasite maintain that very close association. It also explains how the same species of parasite with a different host over here maintains that association. That's coevolutionary arms race. That's coevolutionary arms race. It tells you nothing about how those associations originated. It doesn't tell you how the same species of parasite can have coevolutionary arms race dynamics in two different ecosystems with two different hosts. And it doesn't tell you how those associations can change. Now, if we're going to talk about climate change, we don't want to base our explanations on a model that tells us how things do not change. This is a model that explains stasis. This explains how the status quo is maintained. And later on, I'll tell you that this is also explains a concept called pathogen pollution. Once a new pathogen gets into an ecosystem, it never disappears. And it doesn't disappear in part because of this, the very strong mechanism for maintaining a pathogen in an ecosystem. But it doesn't explain where the associations come from in the first place, so it cannot explain where new associations are going to come from or why they're going to happen. So if we're going to try to be proactive about climate change and emerging diseases, we can't use this. And I'm suggesting that, in fact, the coevolutionary arms race involves magical thinking. And the magical thinking is this. Okay, climate change, there's something called climate change. And there was an entire medical conference at UCLA Medical Center about 5 years ago. And the theme of the conference, all medicos, all doctors, right? No parasitologists, no biologists. And the theme of the conference is, how is climate change causing genomes of pathogens to change in particular ways that increase their pathogenicity and increase their ability to get into new hosts? Okay, now, it's possible that Darwin was wrong. It's possible the last 150 years of evolutionary biology has been wrong. It's possible that the core concept of molecular biology, that information flows outwards, is totally wrong. And it's possible that there's something about all the extra carbon dioxide in the atmosphere now that's causing specific genetic changes in the genomes of parasites and other pathogens, only in the parts of the genome that deal with host switching and pathogenicity. That's possible. It's also possible that pigs can fly. It's also possible that George Bush and Dick Cheney will someday be tried as war criminals. None of that's good. It's all magical thinking. I know that. I would like to see those guys in The Hague. It's not going to happen. There's the same problem with the enemy-free zone. I mean, the bottom line is there are no enemy-free zones on the whole planet. There is no place on this planet where a species of host can go that is not going to find something that's going to infect it. The other thing about the enemy-free zone is that it suggests that you are at greater risk living in an area where you encounter pathogens that your species has been associated for millions of years, that you're at greater risk for disease there than you are at moving into an area where you're going to encounter pathogens that you've never seen before. So the idea is that there's a greater risk of disease in an area where there has been a long history of the evolution of resistance than in an area where there's been zero history of selection for resistance. That's not just magical thinking, that's just wrong. That's what I said. It sounds like a neat idea, but then you think about it for a microsecond and go, no, that's just wrong. So this one, I mean, the coevolutionary arms race is an interesting thing, but this enemies-free zone, we can just get rid of that now. And the data don't support it either, which is also convenient. So here's a little phylogenetic thought experiment. This is really beginning to bug me. How can extreme resource specialists host switch quickly? And what I'm going to show you now are some cartoons, okay? And these are cartoons of host phylogenies with a parasite. We'll call it parasite 1 here. And see, there's just this one thick line there, and that says that that particular species of parasite is only associated with that particular species of host, and that's because there's a set of resources represented by that thick line that the parasite requires, and only that host species has. Now, what happens if we have a situation in which replication rates are higher than mutation rates? Okay, if replication rates are higher than mutation rates, that means that the vast majority of characteristics that any one species has are shared with other species. And that's the basis of phylogenetic analysis. Phylogenetic analysis works because replication rates are higher than mutation rates. So that means that the characteristics that this species of host has, many of them may be characteristics that are also shared with other closely related species. Now, if we find a situation in which only this species of host has that parasite, but we know that these other two species of host have the same resources that this host has, we can predict that if either of these two hosts come into contact with that parasite, the parasite's going to say, oh, more habitat. The parasite's not going to need to evolve anything at all. There's not going to be any need for any genetic revolution. Because from the parasite's perspective, these are all the same thing. We recognize them as 3 different host species, but the parasites are not tracking the host taxonomy. They're tracking the host biology. They're tracking the host resources. That gets even trickier than that. Here's a situation, now we have the same sort of thing, it just looks different. But this is a situation in which these 3 species of hosts all share the same set of resources because of conservative evolutionary history. But in this case, that set of resources is very old. It's what we call a plesiomorphic set, or an ancestral set of characteristics. And as a result, these 3 species of hosts are not, quote-unquote, closely related. So this is a classic case in which you say, oh, well, here's a generalist parasite. Because it's in 3 different hosts that are not closely related. Well, the reality is that this, even though this picture looks different, the reason all 3 of these hosts could host that parasite is exactly the same as this one over here. It's common evolutionary history. So, is this a generalist? And that's a specialist? It's exactly the same thing. So, having an evolutionary perspective on this ecological phenomenon makes us really have to reconsider this whole concept of host specificity and host range. And here's a case in which whatever it is that the parasite needs to survive has evolved convergently in two different hosts. So now these hosts have nothing to do with each other. And yet, the parasite can utilize both of those hosts for the same reason. So it turns out that no matter what kind of phylogenetic diversification patterns you see, there are ways in which host range is a completely unreliable indicator of whether the parasite is a generalist or a specialist, because in all of these cases, the parasite is an extreme resource specialist and can host switch really quickly if ecological contexts change. So evolutionary conservatism, a change in local ecology, that's all you need to have an emerging disease. You don't need all of this magical genetic revolution and genomic, this, that, and the other, and pathogenicity genes and things like that. Enemies and arms races. Well, one of the corollaries of ecological fitting is this concept that some ecologists have developed now called sloppy fitness space. And it basically says there's a lot of room there. There are lots of susceptible hosts in the world, and most of them are not hosting any particular parasite at any one time for a lot of different reasons. Local ecologies are different, so that some susceptible hosts simply do not come into contact with the parasites. And in other cases, it's a question of geographic isolation. But the idea is that there's a lot of host habitat out there that's not being utilized right now. And ecological fitting then invalidates the notion that the number of hosts utilized by each parasite is a good indicator of much of anything, other than this is what is happening right now. But it doesn't tell us very much about whether or not the parasite's a generalist or a specialist. Or another way of saying this is that you can be an extreme specialist and host switch really quickly if the context of your life changes. So here's an example. This is all just not monogenes. There's a couple of nematode groups from great apes. But this was a study that we did based on a couple of groups of nematodes living in great apes that are supposed to be among the primary examples of the co-speciation paradigm, where the host and parasite phylogenies do this. This is a group of pinworms and a group of hookworms. And this diagram, again, there are circumferences of the world monkeys here. Now, this diagram is not an attempt to represent the host phylogeny using parasites like they were taxonomic variants. This diagram is a summary of the history of the diversification of the hosts and the parasites. So 3 different groups of organisms, 2 groups of parasites and 1 group of hosts. So this is a summary of the way in which all 3 of those groups have diversified together. The heavy lines represent the places where the host and parasite phylogenies are the same. And the thin lines represent all the host switches. Now, this is basically only about 50% host switching and 50% co-speciation. But remember that this is one of the examples that is supposed to be an example of 100% co-speciation. And some of the methods of analysis for comparing host and parasite phylogenies have been calibrated using this data set as an example of 100% congruence. And it's simply not. Now, when you start to look at the host switches in this database, what you find is that of all of the host switching events on that picture of diversification, all but one of them represents a host switch among old world monkeys and great apes. In other words, among closely related hosts. There's one example in that entire one of the hookworms is an example of a host switch from primates to rodents. That's the only case where we actually have evidence that maybe something really interesting happened genetically, where the parasite is now in a host that's very distantly related from the original host. So a switch from primates to rodents. The rest of them are just primates and closely related primates. So most of those host switches are due to ecological fitting, not to some kind of evolutionary revolution. So maybe one of them was due to the evolution of new host utilization capabilities. So not only do you have lots of host switching, but most of that host switching is just ecological fitting. So there is a prediction then that says that host switching is not sort of a gradual stochastic thing. Host switching is not something that just happens by accident, it's sprinkled throughout history. What we're finding, and Eric Hober has documented this from the Cretaceous, we have examples of this in studies from 150 million years ago all the way up to 15,000 years ago. And it's the same pattern at every scale of time. And that is almost all of the host switches that we document come in bursts. And each one of those bursts is associated with a historical episode of global climate change. So what's happening now, no matter what's causing this episode of climate change, the way we are seeing an increase in emerging diseases is just another example of a repeating evolutionary phenomenon. We have seen this, evolutionary biologists have seen this picture before. And the reason that these host switches happen is that one of the things that happens during climate change is that species begin to change their geographic ranges. Okay, we have this very heroic, the neo-Darwinian paradigm has this very heroic view about evolution, and that is, you're in one place, you become perfectly adapted to the conditions, and then the environment changes in those conditions, and you stay there, and you adapt to the new conditions, and you produce these evolutionary modifications that allow you to stay there. But that's not what the fossil record says. What the fossil record says is that when the climate changes, species try to leave. If you're a wet-adapted species and your habitat begins to dry out, you leave. If you're a dry-adapted species and your habitat gets wet, you leave. And so you find the wet-adapted species moving out, the dry-adapted species moving in. And there's this very nice lag period. These kinds of things happen. It's not that the old guys move out, leave an empty space, and then the new guys move in. Things do this, and as they move, they overlap. That's when you start to mix the possibility of parasites. That's when you start to see parasites that you are susceptible to, but you've never seen before in evolutionary history. Now, we do this sort of thing. Every time we introduce a new species into a new part of the world, we're just doing a little rapid experiment in that kind of evolutionary dynamic. Now, what drives, this is what we would call exploring sloppy fitness space. In other words, what allows parasites to come into contact with lots of new hosts that they're susceptible to? Well, there are basically two things that allow this. One is climate change, and one is species introductions. Okay, so if you don't want to have a lot of emerging diseases, don't have climate change, and don't introduce species to new places. Oh, too late. Okay, so we've done this to ourselves, right? I mean, part of this is what evolution does, and part of it is we're helping it, we're making it worse. Okay, so understand that this is the consequence of what we do. Why do we have Ebola? We have Ebola because they're human beings going into parts of the African rainforest where they've never been before. And they're coming into contact with pathogens that have been sitting there for millions of years in other warm-blooded organisms. Human beings walk up, go up in the trees, cutting the wood, and the insects that have been transmitting that virus go, oh, here's another warm-blooded host. The difference is that warm-blooded host has no history of selection for resistance. So they come back down out of the trees, they go in their villages, and everybody dies. It's evolution. The last part of this resolving the parasite paradox is this thing that's called the taxon pulse. Okay? Now, in an area called historical biogeography or holistic biogeography, there is a paradigm that says that all geographic distributions of related species are the result of regressive geographic isolation. There you go. Okay. We can find correlations between deep speciation events and continental drift, uplifting in the Andes, sea levels going up and down, isolating things. But the problem with that particular paradigm is that it's incomplete. See, in order to be isolated sequentially into a number of differentiated species that are allopatric, somebody had to have a big geographic range initially. And if this only happens once, then you had, once upon a time, more magical thinking, there was one species of something that was everywhere on this planet. And since that time, it's just been progressive vicariance, carving up. And so today, we have a world in which every piece of area on this planet is either occupied by only one species or by one clade. Now, does anybody know of any part of this planet where that's true? No. And the reason for that is that the geography is far smaller. The geographic space is far smaller than the informational space of evolutionary diversification. So, using a sort of a Microsoft Word analogy, this planet has been overwritten many times by evolutionary diversification. And once again, if you use methods of analysis that don't allow you to see anything but vicariance, it looks like the whole world is just vicariance. But when you use methods of analysis that are sensitive to both geographic expansion and isolation events, a very different picture emerges. And we have reanalyzed all of the classic cases, published classic cases of vicariant biogeography, all of them. 100% of the cases that have been published as this shows the vicariance, including my own, from 20 years ago. Every single one of them shows the same different pattern, and that pattern is geographic range expansion, isolation, range expansion, isolation, range expansion, isolation. And that's what Terry Irwin called the taxon pulse 40 years ago, and it was ignored because we were all so focused on vicariance. So you have the taxon pulse, geographic expansion, isolation, expansion, isolation, expansion, isolation. You have generalist to specialist, generalist to specialist, generalist to specialist, and back and forth. So this is how you have, over long periods of time, you have parasites exploring the world. And all they need is the opportunity to go someplace new, where they're going to find a new host that's phylogenetically very similar to the old host, and they'll survive just fine. That's why Eric Hoberg has discovered many species of parasites living in marine birds and marine mammals in the Arctic that are far older than their host groups. Most of the cestos that live in marine birds and marine mammals are millions of years older than the birds and the mammals. This mass extinction, the KT boundary, that mass extinction, the dinosaurs finally disappeared, except for the birds. Lots and lots of things went extinct. A lot of parasites survived. Parasites probably survived the great KT boundary extinction better than their hosts because of ecological fitting. And that may explain why we have some hosts that are just loaded with parasites. Lots of parasites made it through, and a few hosts made it through, and so those are the hosts that were lucky enough to receive lots of parasites. So we'll now look at the biogeography, and this again is another diagram, And you see here, AS is Asia, Africa, Europe, Asia, the Americas. This is a diagram that shows the combined evolutionary histories of hominoids, elephants, and hyenas since the Miocene. So this is a combination of living and extinct species. Hyenas, hominoids, and elephants. And all of these thick lines represent cases in which all three of those groups had exactly the same geographic history in their phylogeny. And then the small lines that are very difficult to see, but there are just a few of them, are cases in which one of those groups did something unusual by itself. But you see that most of this, if you say, was there hominoid evolution? Well, no, not really, because hominoid evolution was pretty much elephant evolution, and it was hyena evolution, and probably everything that the hominoids and the elephants and the hyenas were eating. But at the same time, recognize that the same geographic areas show up over and over and over again. So what you have is the geographic distributions are complicated. But all three of these major groups of organisms have experienced the same complicated evolutionary history. And it's a taxon pulse that has isolation in Africa and then dispersal out of Africa into Asia. Isolation in Asia, dispersal out of Asia back into Africa. Back and forth and back and forth. That explains why if you want to find, if you're a paleontologist, you want to find the largest concentration of species of extinct elephants or hyenas, you go to Central Asia, because that was the highway, back and forth and back and forth and back and forth. So what you have is this nice taxon pulse, and the parasites in the primates show the same picture. They're part of that. They were carried by their host back and forth and back and forth. So when an African primate disperses out of Africa into the middle of Asia and takes some parasites with it, those parasites then go into local hosts, local primate hosts. And it goes back and forth and back and forth. Pretty soon, everything's all mixed up. But it's a coherent evolutionary picture, as long as you recognize that what parasite evolution is about is a combination of oscillations between being a generalist and a specialist, ecological fitting, maintaining the ability to get into hosts that you've never been exposed to before, and the underlying biogeographic dynamic of taxon pulses. And this creates an enormous amount of potential. And so now, when we start explaining parasite diversity, we have to begin with an explanation based on episodic climate change. Even if we're dealing with a parasite group that's 500 million years old, most of the major phylogenetic events are going to be associated with episodes of climate change. Most of the host switching events are going to be associated with episodes of climate change, either isolation or expansion. Host-host interactions, well, that's also part of the climate change dynamic. That's part of the taxon pulse. Parasite evolution. Our parasites do evolve. They're specialists, but they do change their microhabitat preferences. They do change their transmission dynamics. And they do that without regard for the hosts. I mean, the hosts are not causing parasites to evolve. Parasites evolve. And just like anything else evolves, and then if they can survive, they survive, and if they don't, well, they go extinct. Parasite-parasite interactions is something we don't talk about as much as we ought to. But if you have a situation in which, as a result of species moving around, hosts coming into contact with new parasites, and potentially bringing their old parasites as well, you have the possibility that suddenly now you're not only going to have closely related species of hosts picking up the same parasite, but you're going to have one species of host picking up closely related species of parasites. So for example, in North America, and in Costa Rica, and in Mexico, and in Europe, and here, and everywhere else, there are large, aquatic, predatory, territorial, aggressive species of frogs all over the world that will have living in their lungs between 1 and 7 different species of trematodes that are all members of the same genus. And they're not sister species. It's not massive speciation in the cosmos. It's mix and match and mix and match. This is a case in which the host, there may in fact at one time have been 3 or, for 7 species of lung flukes, there may have been 7 species of hosts. One of them survived the KT extinction. And all 7 species of parasites survived too. So that's another thing that we need to consistently talk about, is that parasites are great at surviving. And when we start thinking about things like biological control, getting rid of parasites, oh, the host goes extinct, the parasites go extinct, it's not true. Parasites are great at surviving. They're really good at surviving. And we have some ideas about what they do that help them survive that may, in fact, inform larger policy issues with respect to how do we deal with climate change, what do we expect is going to happen. So, sorry. Here's the deal. If the parasite species is the evolutionary resource, if the host species is the evolutionary resource for the parasite, then you have one view of the world. The parasites are just like another taxonomic character of the host. And in a sense, they have no evolutionary capabilities of their own. But if the hosts have the resources that the parasites need, as opposed to saying the hosts are the resource, if the hosts have the resource, then those resources are inherited characteristics that can have all of this complicated phylogenetic distribution out there, and the rest of this then flows from that. And then all you need to do is to have climate change and species moving around to produce an enormous number of emerging diseases. And against that backdrop, the concept of emerging infectious diseases simply is the current manifestation of a recurring evolutionary theme, which is when you have climate change events, you have a lot of host switching as a result of geographic range changes and ecological fitting. Now, obviously, this is not the kind of perspective that pharmaceutical companies use to make a lot of money. So pharmaceutical companies, of course, want every time the same pathogen shows up in a new host, it calls for massive amounts of government support for genomic studies and new vaccines and things like that. These little experiments in natural selection. But emerging infectious diseases are not caused by genetic changes caused by climate change. Genetic differences in host switching populations of parasites are due to founder effect, not to some sort of genetic revolution. Pathogenicity. When a parasite switches to a new host, there is often acute disease for a fairly short period of time, a limited number of generations. And that's because the new hosts, no matter how similar they are to the original hosts, the new hosts have never had a history of selection for resistance, because natural selection cannot work on something that has not happened. You can't have selection for resistance until you have exposure. So all of those susceptible species of hosts out there that have never been exposed to a parasite, every single one of them is a candidate for an emerging disease, an initial acute disease relationship, until evolution kicks in, until selection kicks in, resistance evolves. And then once that happens, the acute parasite disease or the acute new pathogen disease becomes a chronic problem. Okay? There are no reports in the papers, in the newspapers, online in North America about West Nile virus. That's great. West Nile virus has been eradicated from North America, right? No. It's still there. It's never going away. Now that it's been introduced, it's never going away. And the reason it's not going away is because selection for resistance has made West Nile virus now part of the evolutionary and ecological background of North America. It's just not an acute problem anymore, so we don't talk about it. It's not a crisis, so it disappears. We don't think about it. But the reality is that if you have 1,000 chronic diseases, the impact on a public health system is just as big as 2 or 3 plagues. And this is where the coevolutionary arms race comes in. The coevolutionary arms race dynamic is what keeps selection from eradicating parasites. The coevolutionary arms race, because parasites are really good survivors. And parasites survive primarily in a coevolutionary arms race dynamic as part of pathogen evolution, the chronic background. And they just kind of accumulate and survive. Hosts come and go, and the parasites survive. It's one of the reasons there's so many species of parasites on this planet. They're really good at living. Now, we of course make it worse. We, as in the pharmaceutical industry, what I call the medical industrial complex. Because what the pharmaceutical industry does is it makes parasites adapt to chemicals rather than host immune systems. And they actually use the drugs to block the parasite and the host from dealing with each other. So you start giving kids antibiotics when they're 3 years old. By the time they're 15 years old, they have the immune system of a 6-month-old baby. And they get sick all the time. Because the effect of all those antibiotics has been to block their immune system from the pathogens. The pathogens are over here adapting to the drugs, which is good business because it means that you need more and more drugs. But at the same time, it's also good business because those drugs block the relationship between the immune system and the pathogen, so the hosts never actually have an opportunity to adapt. The Romans had an expression, quis custodes ipsos custodia, who guards the guardians. Okay? And this is the reason why we have this belief that there should be civilian control of the military. Anytime you don't have civilian control of the military gets out of control. And it's the same thing here. I mean, who's watching the pharmaceutical industry? I mean, we're trusting these people to take care of our children's health. But their greatest economic incentive is to do things that evolutionarily have exactly the opposite effect. This is a real problem. That's one of the reasons you don't find the pharmaceutical industry helping with the biodiversity crisis very much, because they're making enormous amounts of money from it. Emerging infectious diseases are evolutionary accidents waiting to happen, and the entire planet is a minefield of potential emerging diseases. The number of emerging diseases is going to depend on how extensive species can move around as a result of climate change and how many species we introduce into new parts of this planet. But there are enormous numbers out there. All of those host switches and the pinworms, the hookworms, in those primates back in the Miocene, those were all emerging diseases in the Miocene. Now they're just part of the coevolutionary picture. But they originated, most of those associations originated as emerging diseases. Also, it turns out that species that disperse well, species that move around a lot, are the species that survive climate change events the best. That's what the paleontologists show us. From 1 billion years ago until the last ice age. Species that have large ranges, large populations, that can move around a lot, those are the species that survive climate change events. Those are also the ones that move parasites. So it turns out that we can't hope that climate change induced extinction of hosts is going to help reduce the number of parasite species. It's not. If anything, it's going to concentrate more and more species of pathogens in fewer and fewer host species. Once again, because our organisms survive better than our hosts. I mean, it doesn't sound reasonable for the way we were taught, but parasites actually survive better than their hosts. There's a reason why biological control has a 100% failure rate. Biological control has never worked. Ever, 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 ever. Okay, there's only one other thing that has the same record, and that is a city saying, we're going to build a big arena, and it's going to bring in a lot of jobs and a lot of performers, and it's going to make a lot of money for the city, and nobody's going to have to pay extra property taxes. Well, in North America, at least, every single city that has done that has ended up inheriting that arena as a money-losing project, and property taxes have gone up every single time. Same thing with biological control. It doesn't work because here's what we do. We have, okay, here's this fruit tree that we've transplanted to Hawaii. Oh, there's an insect in Hawaii that's eating this fruit tree. Huh, what are we going to do about it? Well, let's go and find out. Let's go back to where that insect came from. Oh, there's a parasitoid in where that species came from that keeps the population of that pest insect down. So we'll introduce the parasitoid over here. And this parasitoid, because over here, that parasitoid only infects that insect. So this is great. This is self-limiting. We'll bring the parasitoid in. It will reduce the population level of the pest insect. Then the introduced fruit trees in Hawaii can grow, and we will have used the introduced parasitoid to reduce the population of the introduced pest insect. And what happens? You bring the parasitoid in. The parasitoid immediately takes off after one of the most important pollinator insect species on the island, because that's also in the range of ecological fitting for it. And in fact, they kind of like that other species of insect. So now you have this problem where, oh, now the parasitoid is a problem, so now, oh, well, maybe we can find a virus that will kill off the parasitoid. And we just do this, and it gets worse and worse and worse. It costs more and more money. And it never works. And it never works because we never take the phylogenetic basis of host specificity into account before we introduce something. It's based on this host range. It's very simple host range. Now, this crisis of ignorance is our fault. It's all our fault. And it's our fault because we've named fewer than 10% of the species on this planet. We've analyzed less than 1% of the species on this planet phylogenetically, less than 5% of them. And do we know anything about their historical biogeography and historical associations with their hosts? And almost all of those have been analyzed using methods that deliberately give us the wrong answer. Because they give us an answer that we're comfortable with because that's what we were taught, but it's not what's really happening. So here's something. This is from a blackboard in Modern Ga. Students from Puerto will recognize this. This is, it's a little out of focus, but this is what is called the classic case of co-speciation. This is a group of rodents, poppy gophers, and a group of lice. And if you go to Ridley's evolution textbook, he has these two phylogenies lined up just like that in a figure, and the caption says, mirror phylogeny of hosts and parasites. And it's just wrong. I mean, it's just not even close to being right. Okay? Here's some co-speciation. Co-switching, co-speciation, co-switching, co-speciation, co-switching, co-speciation. It's a taxon pulse. Half of those associations are host switching, half are not. There's about 50% co-speciation. But that's supposed to be another case of 100% co-speciation. And it's just not. I mean, it's really not. And not only is it not co-speciation, but what it really shows is this general phenomenon. And so now what we need to do is to ask what the periods of time were on this. What episodes are associated with the co-speciation? What episodes are associated with the host switches? What's going on here? And we know a lot about the geological and climatological history of North America during the time period that these groups were evolving. So we have, I mean, in a sense, we have to stop denying reality to ourselves. We have to stop telling ourselves it's all vicarious association when the data don't support it. And when the reality, what the data are really telling us is something that makes our organisms and understanding our organisms really useful for debates about climate change and emerging diseases and biodiversity. Evidence is never enough. Well, it's been good enough. You know, those models, they're good enough. So I call that the dirty Harry criterion. You know, a man's got to know his limitations. You need to be really, really skeptical about the models that we have now because in part, models can be developed to give you a false sense of security, make you feel good about yourself. So if there's ever a time to think outside the box, if there is a biodiversity and emerging disease crisis, then time is critical. We've been screwing around for a long time, and we don't have that much time. We can't continue to keep doing things the way we've been doing things, especially among academics. We have to cooperate. Now, there is time to do that, okay? Don't be afraid, we have a plan. We can't stop or reverse climate change, but we can adapt to it. And parasitologists deal with the greatest adaptational systems that evolution has ever produced. The systems that we work with are so good at adapting that they survive better than their hosts. It doesn't sound logical, but it's true. I mean, they're phenomenally good at surviving. And this is just another version of this old saying, think locally, act locally, but now we say, start now. And Eric Oberg and I think that parasitology, not just from the standpoint of what we can add to the discussion of emerging diseases, because, let's face it, bacteria, viruses are not that interesting compared to the organisms that we study. And yeah, they're important and they cause people to hemorrhage and die, and it's very, very spectacular. But the reality is, bacterium is, it's transmitted, it comes to any of our parasites, anytime we report one of them, behind the name that we assign to that is an enormous amount of ecology and evolution and natural history that adds the appropriate biological context to what's going on in terms of climate change. And I know that the virologists and the bacteriologists have, get most of the publicity about this, but that's because they're all funded by the pharmaceutical industry. And I'm not suggesting that we have some big revolt against pharmaceuticals and we stop taking medications or anything. What I'm saying is we have critical additional information to offer, not in competition with the pathology people, but in cooperation with the climate change, biodiversity, emerging disease people that are looking at larger scale problems of issues of how much of the biosphere is going to survive, how much of it is going to change, and how is it going to change. I think I think we have an opportunity to not only do something for humanity, but also do something for our discipline. And I don't know if, for example, in Brazil, I don't know if you have the same problems with membership in the parasitology societies as in North America, but when I became a member of the American Society of Parasitologists, there were 3,500 members of the society. There are now 800. And it's not because parasites are less significant. It's because we haven't done a good job of telling the world why what we study is so important and important to them. Okay. Thank you very much. I never told anybody what to do with one machine. You're going to make it for a cocktail, so I'm going to open for questions. Danny's going to be here 12 a week.
Luciana, in black. She's going to help you putting your presentation in the computer. And I'll invite you to go to our welcome cocktail. Welcome to all of you.